So let's start the morning session of the second day of this workshop. My name is Shu Watanabe, the session chair. So we have 3 talks in this session. The first talk is about strong Converse bounds for compression of mixed sources states, and given by Zahra Khanian. So please start your talk.
Thanks for the introduction, and also I'm thankful to the organizers for accepting my talk to this workshop. I'm going to talk about the strong Converse bonds for compression of mixed states. I believe that the audience in this workshop are quite familiar with a lot of stuff, but I thought maybe it wouldn't hurt to just introduce some more background. So basically, if I want to talk about quantum data compression, it is pioneered by Schumacher. And Schumacher took the idea from Shannon's compression. Basically, Shannon defined a statistical classical source as a random variable, and then Schumacher generalized this notion to quantum version as an ensemble of pure states. So he defined a quantum source as an ensemble where pure quantum states are generated with some probability distribution. And in the setup that Schumacher considered, he considered the asymptotic version. So suppose that there are n IID copies of the source state. Each of these sequence of states are generated with product probability distribution. And these quantum states are fed into an encoder, which is a CPTP map, a general quantum operation. And these input data are mapped to some other quantum system, let's call it MN. And the goal is to minimize the dimension of the compressed information MN as much as possible. And then this data is transmitted to a decoder using a noiseless quantum channel. And this decoder wants to recover the original data with some measure of accuracy so that the output data is close as much as possible to the original data. And the figure of merit that Schumacher considered was the average error or average fidelity, which is defined as the averaging over the probability distribution for the input and output states and the fidelity between them. So essentially, the interesting variable here is the dimension of the system compressed information MN, and the rate of the compression is usually defined as the dimension log of dimension of system MN over N, which is the number of the copies of the source. And Schumacher essentially proved that the optimal compression rate is equal to von Neumann entropy of the source. So we know that strong Converse property holds compression. A strong Converse essentially means that, so suppose that we have the optimal compression rate. And if the compression rate is just a little bit below this von Neumann entropy, then it has been shown that the error converges to 1, and it suddenly jumps to 1. So this is called the strong Converse property. And first off, it was shown by Josa and Schumacher in 1994, assuming that the decoder has a specific structure, that is, the decoder can only take unitary operations, and then later fully by Winter, when the decoder can be any general quantum operation. So, okay, then the notion of quantum source later was generalized to the ensemble of mixed states. So suppose that there is an ensemble of mixed states, and if the indexes of these ensembles, the states from these ensembles are not known to the encoder, this is called the blind version, actually. This is as opposed to the case when the encoder knows the identity of the signals from the ensemble, which is called the visible version. So blind version was studied by Koshi and Emoto, and it's been shown that the optimal compression rate is equal to for Neumann entropy of some subsystems of system A, which is called Cauchy-Emoto decomposition. And in a visible case, it was first shown that the optimal compression rate by Hordetsky as some regularization variable, and then Hayashi showed that this is actually equal to regularized entanglement of purification. So it's also worth mentioning that if we have ensemble of pure states, then it doesn't matter whether it's a visible or blind scenario. In all cases, the optimal compression rate would be equal to the von Neumann entropy, and a strong converse holds anyways. So now the question would be, if we have a compression of mixed states, does the strong converse property hold in this scenario or not? I mean that are we going to have this sudden jump in error if we go below the compression rate or not? So maybe before talking about the results in this regard, this was the question for this talk that I'm going to address. It's worth mentioning some other scenario which is very close scenario. Just there is a small difference which is called the rate distortion scenario. So suppose that we have exactly the same setup as blind and visible compression, but here instead of like having the fidelity or the error for the blocks of states, which is defined here, we compare blocks of input and output data. If we just compare each copy of the input and output data, which is called local error or per copy error, then we are not going to have this sudden jump. Actually, we are not going to have this strong converse property. And actually, we can show that, that there is a trade-off between rate and error, and we can reduce the compression rate in expense of having larger error. This has been shown in a separate work by me, Kotai Kroiba, and Debilium in a recent work. So, okay. Maybe also I can just quickly review some notions that I'm going to use. So the Rayleigh entropy is for a quantum state for alpha between 0 and infinity, excluding 1, is defined as this expression here. There are some interesting properties. The most important ones are listed here that I'm going to use. So the first off, if alpha converges to 1, it's been shown that the Rayleigh entropy converges to von Neumann entropy. The second one is that the Rayleigh entropy is bounded by the local dimension of the system. And the last one is additivity over tensor product states. So for the sake of this talk, I'm going to talk only about the visible compression case because the time is very limited. So this is the setup that I'm going to remind in this slide. So we have this ensemble of mixed states fed to encoder, and the index are being seen by the encoder as well. And as I mentioned before, the optimal compression rate is equal to the regularized entanglement of purification. And by regularization, we have, I mean this quantity here. So we have some limiting quantity here. So for n convergence to infinity, if we have the entanglement of purification between an and xn, which is the classical variable of the ensemble, then the regularized version is defined here. Also I have to talk about the entanglement of purification. This quantity was defined by Terral et al. In 2002. So suppose that we have some bipartite state rho AB, and suppose that we have its purification, that is the system R is the purifying system, then the entanglement of purification is defined, suppose that by applying a CPTP map only on system R to obtain a system E, for example, in such a way that the entropy of system A and E together, or B and E together, is minimized. This is the notion of the entanglement of purification. And in order to obtain the strong converse bond, I have generalized this notion to the Rayleigh entanglement of purification. So suppose that we have still the same bipartite state and consider its purification. We have exactly the same minimization, but there is one difference, that instead of minimizing the von Neumann entropy, the Rayleigh entropy is minimized here. So still, there are important questions regarding some properties of entanglemental purification. The most important one, which is not known so far, is that whether the entanglemental purification is additive over tensor product states. And also, I also faced the same question here, whether the Rayleigh entanglemental purification is additive over tensor product states. This, if it is shown that it's additive, it's going to be very useful in many different situations. So similar to the regularized entanglemental purification, I defined the regularized Rayleigh entanglemental purification by taking into account many different copies of the state and averaging over n in the limit of n going to infinity. And I call this quantity the regularized Rayleigh entanglemental purification. So for the normal one, actually, by normal one, I mean the Rayleigh entanglemental purification and its regularization. I have shown in the paper some useful properties. So we can show actually both of them are decreasing with alpha. The normal the Rayleigh entanglemental purification is continuous in the between 1 and infinity, and also it is continuous from right at 1. So this is quite an interesting property. Whereas for the regularized version, it's very difficult. It's not actually easy. At least I don't know how to prove it if it is continuous from right at 1. And there's many other quantities actually in information theory that the regularized version is not known to be continuous or not. And showing continuity for this kind of expressions are very important, and there are many that they are still not known whether they are continuous or not. So this is the important open question here that I indicated in blue. And also the other point that I would like to mention is that if we can show the additivity for the Rayleigh entanglemental purification, then we can show that it is continuous with alpha, because it's gonna follow from the continuity of this normal Rayleigh entanglemental purification. So this is the main theorem of this paper. So basically we can show that the average fidelity of the compression task is bounded like this, which is exponential with respect to n and this alpha quantity. And there is this regularized Rayleigh entanglemental purification. So I use this main theorem and some properties of the regularized Rayleigh entanglemental purification, such as the fact that it is decreasing and also continuous for alpha greater than 1, to show that for any rate below this limit point, the fidelity is gonna converge to 0. This is stated in this lemma. So if this was continuous, then we basically were down, and we have been able to show that the strong converse holds. But since we have this this quantity that we don't know whether it's continuous or not, there is a gap still to show that the strong converse fully holds. I mean, by fully, I mean that in the whole range between the regularized entanglemental purification and 0. However, still we can obtain this bound, and if it is continuous, then we are completely done with showing the strong converse for the visible compression. So I thought maybe it's a good idea to give some hints about how I prove this theorem. So one of the main ingredients that I use in my arguments is this lemma, which is quite old, actually from Van Dam and Hayden from 2002. So if we have any quantum states, then we can relate their fidelity to their Rayleigh entropies as this equation, as shown here. So if beta is in this interval between 1/2 and 1, and if alpha is a function of this beta, then we can show that the fidelity is bounded like this. So this is, as I said, one of the main ingredients that I use to show the strong converse property. And the way I use it is like this. I have shortly mentioned it here. So I have the decoded states together with the environment system of the decoding CPTP map, and then I replace it with the entropy of the system itself without the decoding, without the original source, and then considering some extension of this state, then I'm going to relate the fidelity of these two states together and prove the strong converse property. So these are the steps that I'm going to explain in this slide. So this is the logout dimension of system MN is the rate of the compression, or sorry, if we have one log of this MN over N, then it's going to be rate. But however, so we have this quantity here. We know that it is bounded below by the Rainy entropy, and I assume that this beta is between 1/2 and 1 in order to use the Van Damme and Hayden lemma. And then if I use just the definition of the decoding isometry, we know that the compressed information is processed by the decoder. And if I just define the decoding as this Steiner-Spring dilation of the operation D, then M is going to be mapped to some system A hat N, which is some guess or reconstructed version of the source, together with some environment system, which appears here. So, and here I basically use Van Damme and Hayden lemma. I replace this system with the original source together with another source, which is basically an extension of this state, and the fidelity of between these two states appear here. And then we know that actually if two states have some fidelity, then we can find some extensions or some purification of these two states in such a way that the fidelity of these extended systems are at least as big as the fidelity of the states themselves. So this is the Ullmann's theorem that I'm using here. And then, okay, and then let's move on to the next slide because I don't want to expand on every single step. So far we have this, the entropy of the original source together with some extension system and the average fidelity which appears in the logarithm here. And then if I take the minimum over all these extensions of this source, then we can basically show that this is equal to the Rainy entanglement of purification. So that is how we get from the Rainy entropy to the Rainy entanglement of purification. Basically is by relating the extension of the source and how minimizing the entropy to the Rainy entanglement of purification. Okay, so, and the final step here is that I basically rearrange all of the terms to obtain this equation that I already introduced in this theorem here. So basically after these steps, we can show that the fidelity is bounded like this. Okay, so if I want to conclude, I would say that in this work, I have studied the strong converse property for the visible compression. As I explained, the visible optimal rate in the visible compression case is equal to the entanglement of the regularized entanglement of purification. I define a new notion which is called the Rainy entanglement of purification and also regularized Rainy entanglement of purification. I mentioned that there is a big question here whether this quantity, the regularized version, is continuous at 1. If it is continuous, then the strong property, the strong converse property holds. So this is the important question that is left in this paper open. So if this equality holds, then we can show that the strong converse property holds. So the other important question that it's gonna help with many tasks in information theory is showing the additivity property. So it's not known so far whether the entanglement of purification is additive or tensor product states. Also, if we can show that this is additive for the Rayleigh entanglement of purification, then it's going to imply that this quantity here is continuous, and then we can show that the strong Converse property holds. So this was for my talk, and thanks for your attention.
Okay, thank you very much for your talk. So let's, yes, Mark, please go ahead to have a question.
Hi, Zahra. Thanks for your talk.
Hi.
So I have a basic question. You're evaluating the entanglement of purification for a classical quantum state, right?
Yes.
So usual entanglement measures are equal to 0 for classical quantum states, but I guess that is not the case for this quantity, right?
No, it's not equal to 0. Okay, let me just bring. Yes, here it's been shown, and no, it is not actually. It's the entanglement of purification is not equal to 0.
All right. Are there classes of states for which you can evaluate it?
So for example, for pure states, we know that the computation is very easy and it's additive and all the properties follow. But as for the other examples, actually there are some examples in some papers that they guess that it might not be additive for the mixed states in general, but other than that, I don't remember right now other examples.
Is it correct that Andreas Wenzer and co-authors had a paper called Additivity of Entanglement Purification Beyond Reasonable Doubt?
Yeah, that's the example I'm talking about, actually.
I see.
So they do some simulations, and basically they say that if their simulation doesn't have errors, then their numerical results show that the entanglement of purification in general, it's not additive, right?
Non-additive, okay.
It's not additive, yes.
Okay. Thank you.
You're welcome.
Okay, any question from this? We still have a few minutes. Well, I have one question. So you said some special case like pure state case, you can compute the exponent. Is it tight in the sense that you can also show achievability for this exponential rate?
Yeah. This rate actually. So if there are some states, for example, for the pure states, we know that this quantity is additive, and then basically we can show that it is continuous with alpha going to 1. And also we know that this rate is achievable. So there is this theorem that I mentioned in the beginning. So the optimal, it's been shown actually in the early 2000s that the optimal compression rate is equal to this quantity here. So basically there are protocols that achieve these rates.
Yeah. My question is, yeah, you can achieve entanglement of purification, but I'm talking about convergence rate. When the rate is smaller than the asymptotic limit, in that case, fidelity must goes to 0. But
okay.
you can also, even in that case, you can also prove achievability. So in that sense, your converse bound, is it tight in some special case?
So,
do you know any idea?
I haven't proved anything regarding that, and as far as I know, it's not been shown. So there's not any achievability protocols for fidelity smaller than 1.
Okay. Okay. Thank you very much.
I have a question.
Oh, yes, Professor Hayashi. Yes.
So I'm slightly confused. You mentioned that you have a result in the case of pure state. Pure state means that in this slide, this rho XA is pure.
Sorry, your voice is not very clear to me. I didn't understand your question.
Maybe you should approach the microphone.
No. So I'm asking, so you are considering the pure state case, okay?
Mm-hmm.
Sometimes. So the pure state case means that this rho is, in this slide, there is rho, this rho is pure.
Mm-hmm. So
Correct?
in the pure state case would be these ensembles that these row X's are pure.
Yes, rho is pure, but I think in that case, not mixed state data compression. This is usual pure state compression. And
Mm-hmm.
in that case, the problem is already solved, including the exponent.
I see. Okay.
Mm,
Yeah. For the
exponent,
pure state case,
in the
yes.
case of pure state case, I already derived the
Mm-hmm.
exponent.
Yes, but for mixed states, there's not any results, right?
Of course, but you write down that pure state case for that by using the entanglement of purification.
Yeah, I mean, if for the pure state case, we can simplify the entanglement of purification. It's going to be
Yes,
equal
you
for Neumann
give
entropy.
that exponent. Strong compass exponent. Yes,
Mhm.
this one is the same as my result.
Mm-hmm.
This is pure state. You also consider pure state case.
So yes, this can recover pure state case.
This
Yes,
is pure state
but this
case.
is just the converse part. It's not the achievability.
Yes, I know. But in my old paper, I derived that kind of strong compass exponent
Mm-hmm.
in the case of pure state. So I'm
Mhm.
asking, this is the same as my result in the case of pure state case.
So you are asking, sorry, can you please repeat again? I didn't understand.
So I'm asking, your this exponent is the same as my old result when the system is pure.
Okay, I see. Okay, I haven't compared it, but I think I haven't compared it explicitly in the paper. But I think yes, it's the exponent is the same. Yes. Yes, but it's a good point. I think maybe I should do it in the paper.
Okay, thank you very much. Any other question? Okay, if there is any other question, let's thank the speaker again. Thank you very much.
Thank you.
So the next speaker is Carly.